So in this video, we're going to look at the other methods of preparing halogenoalkanes. In the previous video, we looked at the detailed practical method of preparing a halogenoalkane from the corresponding alcohol using a hydrogen halide such as hydrogen bromide, and that particular preparation you need to know in a lot of detail. Quite often details of it will come up maybe on your practical theory exam, something like that. But there are a few other methods that you need to be familiar with for preparing halogenoalkanes. They are found on page 17 of your notes, and we will go there now. So over on page 17, we see the second method for preparing halogenoalkanes, remembering that the first was that big long method that we've just looked at, preparing a halogenoalkane from the corresponding alcohol and hydrogen halide. The good news with these methods is that they are a lot less detailed. You'll be glad to hear, and you don't need to know lots of practical details with them. Method number 2 does involve an alcohol as well, but a different reactant of PBr5 or PCl5, depending on whether you want to have a bromoalkane or a chloroalkane. Obviously using PBr5 if you want a bromoalkane and PCl5 if you want a chloroalkane. These chemicals are called phosphorus pentabromide or phosphorus pentachloride. And we'll actually study this reaction in our alcohols topic. This is a reaction of alcohols that we study. But the product of this reaction is a halogenoalkane, and so therefore this is a method for preparing halogenoalkanes. Essentially what happens in this reaction is the OH group from an alcohol, if you remember it's the basic structure of an alcohol from GCSE and what we studied in that previous method, alcohol group is swapped for either a bromo or a chloro group. Okay, so we've got an example here of the same halogenoalkane that we were preparing in method number 1, that detailed method, 1-bromobutane. So essentially you take the corresponding alcohol, so what we mean by that is just the alcohol that it just links with the halogenoalkane that we want to make, has the same structure of the halogenoalkane that we want to make, that, but just with an OH group instead of the halogen group. So what happens when phosphorus pentabromide, for example, reacts with butan-1-ol? Well, essentially the OH group is swapped for a Br, as you can see in the formula that I've just written, and that is 1-bromobutane. The side products then are phosphorus oxybromide, POBr3, and then if you think about what we're left with, the oxygen from the OH group has been incorporated into this phosphorus oxybromide. If you think about the bromines that we had 5 on the left, we've got 1 here and 3 here, that's a total of 4, so we've got 1 more that we need to have account for, and we've got an H in our alcohol as well. So actually the HBr, so the hydrogen from the OH group of the alcohol and the last remaining Br from the phosphorus pentabromide makes HBr. So if we want to think about the observations of this reaction, phosphorus pentabromide and phosphorus pentachloride are yellow solids. So we'll see that the yellow solid disappears. Will be one observation. If we think about our products that are being formed, we can see that HBr is being formed, and we know that HBr from our halogens topic, it appears as misty fumes. So misty fumes will be released. Other observations are that heat is released, and this is a vigorous reaction. This is a reaction we actually have to take place in the fume cupboard. So if you're ever asked to do this in a practical exam or anything, it can be quite a common one because it produces those misty fumes and fizzing, because we've got a gas being produced in solution or within a liquid. But phosphorus pentabromide and phosphorus pentachloride are toxic, so it needs used in a fume cupboard. You'd have to use gloves to handle it and so on. But as I say, we're going to look at this reaction again in our alcohols topic, but for now know that it is a method of preparing halogenoalkane from the corresponding alcohol. However, it is not that often used, as it results in poor yields. As it says below here in your notes. So method number 1 is preferable over this method. And then the next two methods of preparation, methods 3 and 4, you've actually already met before. So this is a nice part of our in organic chemistry where we start to see the links between the topics and the links between the different families that we have. Because when we studied alkanes, we saw that they reacted with halogens in that photochemical substitution reaction to give a halogenoalkane and a hydrogen halide. So for example, one of the reactions we looked at was chloromethane being formed from methane and chlorine. So we would have had CH4 reacting with Cl2, and what happens in this photochemical substitution is one or more of our hydrogens from our alkane is substituted by a halogen atom. So let's just write the equation for the mono substitution. So that would be where one of the hydrogens is substituted, so we're down to 3 hydrogens, by a chlorine atom, and therefore our other product is HCl, the hydrogen that has been lost from the alkane and the other chlorine atom. This reaction proceeds via a free radical substitution mechanism, which we looked at in a lot more detail in our alkanes notes. So that idea of taking our chlorine molecule and making it into 2 chlorine radicals using UV light, and that reacting with the methane and so on, your initiation, propagation and termination reaction. So look back to your alkanes notes for more detail on that. But notice how in this reaction we have formed chloromethane, which is a halogenoalkane. So halogenoalkanes can be made from alkanes reacting with a halogen under that free radical substitution mechanism, and that must be done in the presence of UV light, because alkanes are generally very unreactive, so we need that UV light to get the chlorine to form radicals and get the reaction going. And then finally, again from a topic that we've seen before, is halogenoalkanes can be made from alkenes and a hydrogen halide. So for example, if we reacted ethene, C2H4, with hydrogen chloride, that hydrogen chloride molecule would add across the double bond, and that would form C2H5Cl, which is chloroethane. That reaction happens via the mechanism of electrophilic addition. Again, that's something you should be able to recall from your alkenes topic. Briefly, let me draw the structural equation for this reaction. So if we had ethene reacting with HCl, you could even test yourself at this point, could you draw your curly arrow mechanism for this reaction? But essentially what happens is that HCl adds across the double bond, so the pi bond of the double bond breaks. So that means each of the carbon atoms can form one more bond, so one bonds with the hydrogen and one bonds with the chlorine. So what we formed there is chloroethane. And that is, again, obviously a halogenoalkane. So while you may not be thinking of, you might not have been thinking it at the time, this is again a method of preparation of a halogenoalkane that we met in a previous topic in organic chemistry, because it was a reaction of another organic family. So you'll start to see the links between your organic families. So that brings us to the end of this section of the methods of preparing halogenoalkanes. So just to very quickly run you through those 4 methods. The first method we looked at in a lot of detail, and it was the method of preparing primary halogenoalkanes from primary alcohols. Essentially, that was reacting the alcohol with hydrogen bromide, forming the bromoalkane. Secondly, we can react the corresponding alcohol with phosphorus pentabromide or phosphorus pentachloride to produce the corresponding halogenoalkane. But as we talked about in this video, this results in poor yields. It is a method of preparing halogenoalkanes, but not often used because it has quite poor yields. Then, from reactions that we met in previous topics, we can prepare halogenoalkanes from alkanes and a halogen, surprisingly enough, given the name of halogenoalkanes, and that reaction is a photochemical substitution reaction. And then finally, a reaction that we studied in the alkenes topic, when we react alkenes with hydrogen bromide or hydrogen chloride, then we will also get a halogenoalkane. So those are the 4 methods of preparing halogenoalkanes that you need to be familiar with.